All right. So let's start the webinar. So today we have the pleasure of welcoming Annabelle, Collin, and Mélanie Prague, who will do a joint talk. So Annabelle Collin is from University of Bordeaux, Institut de Mathématiques de Bordeaux, and Inria. And Mélanie Prague is from INSEAM, I think. And
yep.
Okay. And so they will talk about how to make the link between data and estimations in COVID-19, right? So, okay, so whenever you're ready.
Thank you very much, Quentin, for inviting us first to talk at this seminar. So yes, as you mentioned, we will definitively talk about how to model COVID-19 and especially the first wave that we had last March. But as a disclaimer, like I really believe that all the results and interpretation we may generate from this work are really important, but this is basically also a huge methodological work on building a new type of estimator that allow to basically estimate parameters that depend on time and for which we don't really know what's the shape of the relation between time and this parameter in dynamical models. So this is really methodological. And as you mentioned, this is a joint work from multiple teams from Inria, so Medisim, System, and Monk. Next slide. So yeah, so this work really started from a very long-lasting collaboration that was built between Annabelle, Collin, and Philippe Moirot on developing Kalman filter-based estimators. And in 2018, we basically met with Annabelle and I explained some problem we had in dynamical model estimated in population, which is with mixed effect models. So I will explain later on what is this specific problem, and we decided to work on this topic. This led to a first publication on that you can find on all. That is about building a new estimator. And then when COVID-19 started, we really wanted to apply this new estimator to the estimation of the effect of lockdown for COVID-19. So we worked together and we really see the benefit of this approach compared to more traditional approaches, and we submitted a paper that you can find on medRxiv on evaluating the effect of lockdown during COVID-19. So next slide. So just a little bit of background, because all this work and a lot of results we will present today really date back May 2020. So right now they can be seen as a little old and exhausted, but still at the time we generated those results, I must recall that SARS-CoV-2 was just new, and we knew that it had a high fatality rate and a quite high infection rate between people, but it was difficult to really know what was the value, which was now a little bit more well known. And also in March, we were during the first lockdown, and now we are speaking about a second and a third lockdown. But we see that a lot of countries, maybe all countries in the world, were implementing non-pharmaceutical intervention with some very less stringent measures such as mask and hand washing, but also up to very stringent measures such as lockdown. So we had a really, really small understanding of the disease. Next slide. So the idea was, so here I just plotted the hospitalization a long time, and we were at the very beginning of this curve during the red period, and we had just a little amount of data, but we really wanted to estimate what is the impact of lockdown. And as you can see here, there is a real inflection of hospitalization curve once we are in lockdown. So what is the effect? And the next question was, next slide. Can we inform from the first wave what will happen next and what will happen in particular now with new interventions such as curfew and lockdown, and how big will be the second and third waves and so on. So how we can inform that using our mathematical models. So next slide. So the thing was really about the data first, because we wanted to do a statistical analysis, and we know that if we have garbage in, we will get garbage out. And at the very beginning of the epidemic, and this is still kind of true, there is a very big difficulty in collecting the data and also giving the data to researchers. And the data we got were public or semi-public, and they were first from multiple sources, with multiple formats, with multiple geographical resolution, and also multiple interpretation. We will see that later. But on top of that, we know there is a lot of background noise. So here you can see there is the percentage of hospitalization data by department a long time. And each black curve represents a different department. And here there is a threefold k-means clustering. But you can see that first, like the trajectories may be very different from one department to another. But also you can see that this is very noisy. This is not a very nice curve. There is a lot of maybe error measurement or reporting measurement. So next slide. So the data we incorporated in this analysis were of 4 types. The first one we had was infection data. So the problem with infection data is that if we were looking at just the first wave, we only had the data from Santé Publique France from March 1st to March 25th. So it's a very short period of time. And then if we want to aggregate data from the whole last year, we can switch to another dataset, which is called CDEP, but this dataset only starts on May 15. So it really raises a problem of partial data collection with change of source and also change of collection mode, because as you know, the testing policy really changed a long time. Then we also had some data, about the Sentinel network, which is about the general practitioner in France and help in collecting how many people have COVID-19 related symptoms. And to finish with, we had some hospital data. So the Sursaut database and the Civic database, which was available later, but you could see that there is basically a very big difference in the 2 databases, and there are some inconsistency. And on top of that, all data were most of the time available at the departmental level or regional or at the French level. So we basically had to aggregate all those type of data with mathematical tools. Next slide. And so what we decided to use was data assimilation. So basically, we will use a model that I will describe later on, which is a dynamical model with mixed effects on parameter, which is somehow just an SIR type model, like extended SIR model. And then we will aggregate all the data that I really described before, thanks to an observational model. And this observational model will really help to aggregate the data and understand which compartment represent which source that I just described. And here, and this is really like the goal of this work, is to really build a data assimilation approach based on sequential data assimilation, sequential and variational sequential data assimilation, so that we can actually estimate the parameter. So we are really trying to do the inverse problem from the data, how we can estimate the parameter in the model, which is somehow different from calibration, which is used by many epidemiologists in France. So next slide. So now I will just describe the model rapidly. So we are using, as I said, an SIR type model. So basically we have susceptibles that can become exposed, and they are exposed because they are in contact with two types of infectious people, either unascertained or ascertained, meaning that they know their status if they are ascertained, or they don't know their status if they are unascertained. And once you know your status, you can maybe hospitalized because you have big symptoms, and whether you are infectious, ascertained, non-ascertained, or hospitalized, you can be removed from the model. So of note, the removed compartments encompass both deaf, really removed people, and death. So, which is probably something that can be extended. So from the literature, we fixed a lot of parameters, but the parameters that will be of very big interest here, because we know they change over time, are B, the transmission rate, and DQ, which is the hospitalization rate. So at which time someone which is tested positive may or may not get hospitalized. Next slide. So on this dynamical model that we have, what we will do is that we assume that there is the effect of the non-pharmaceutical intervention, and in particular the lockdown. And this effect will really apply on the parameter B, which is a transmission. And one of the major contributions of this work is that basically we didn't know at first what was the relation between time and this transition. We could think that once there is a lockdown, there is just a step function and the transmission changed to something else, but more probably you may have something which is with multiple steps or maybe even smoother, like a sigmoid function. And this has to be inputted in the model so that you can actually estimate the effect of lockdown. So, and this is what we do here and we build. So as I mentioned, on the parameter of the model, we do apply a mixed effect model, meaning that for each region, we basically assume that the transmission, the base transmission, has a different value. And the discrepancy from one region to another region is actually normally distributed with a random effect, which is normally distributed. And this is really which will allow that with the same mathematical model, we actually do have very different epidemic trajectories between one region to another region. So this is the core. And here again, the transmission here, you see that it's more difficult to write it, and this is spelled out as a parametric function that will be inferred using Kalman filters. Next slide. And to finish with, so I presented all the data we had, and so we had to basically link this data with the parameter of the system, and this is what we will call the observational model. And so basically we had the incident number of cases tested positive, which can be seen as the instant number of new infected people, which is called RE over DE. And you can spell out the same exact way, the incident number of hospitalized, prevalent number of hospitalized, prevalent number of cases, and the number of deaths. And this is basically all those indicators that will be aggregated so that we can perform estimation. So I think I'm done with this.
Yes,
and
thank
now
you, Mélanie.
We'll go to the methods.
Okay, thank you, Mélanie. And now I will continue and I will focus on our data assimilation strategy. So our objective is to minimize a criterion with respect to the uncertainties under the constraints of the model dynamics. If when Gaussian laws are considered, this corresponds to classical least square minimization. So the first part here concerns the uncertainties priors, the second part, the model error, and here it's a comparison between the observations and the solutions of the model. So in the most classical method, the minimization of this criterion is done by several simulations of the models, and at each iteration, the value of the parameter changes, and we converge to the target systems given here in blue. When considering a sequential approach, the idea consists in correcting the dynamics by a feedback based on the discrepancy, combining the data and the model state. So in this case, this means that we will add a new term here, which is the gains observer. And this means that we will only one simulation is done, and this simulation will converge in time to the final estimation. So when we do that, the parameters have a dynamics too, as you can see here. So more precisely in this work, we will consider a reduced order version of a population and something Kalman filter. So many words. So I will explain in that follow first the population criterion that we have defined. I will introduce the Kalman filter in a linear context, and I will present the unscented Kalman filter. And at the end, I will also present the reduced order version of our population Kalman filter. So first of all, the population approach. This approach consists in compensating the lack of data by an available population. So for example, when we consider mixed effect approach, we will pull all the patients together and we will estimate a global distribution of the model parameters in the population. More precisely, we will decompose the uncertainties into two parts, a third part which concerns the fixed effect in the population, and a second part which concerns the mixed effect of the population. This means that our criterion will be will have two terms for the uncertainties pairs. These new terms, these two new terms. So if we assume that the population shares the same mean value defined just here, we can rewrite this criterion as it is done here. And by doing some computation, we can rewrite this criterion, this one, sorry, and we can obtain a classical estimation framework. I mean that this new criterion is also a least square minimization under some constraints corresponding to the dynamics of the solution. You can see that every terms contains all the population that we are considering here for the models, for the observation operator, and also for the noise, the error model noise that we can consider. The key of uncertainty modeling is that the matrix here, P0, which is the covariance matrix, couples the population's members, since we don't have only one diagonal, one block diagonal matrix, which just combine all the population. We really have a coupling, which is due to the fact that here the terms contain the P0 matrix combined all the patient or all the region or the department of the population. So concerning the Kalman filter, I will explain it first in a linear context. So if I, if I consider a least square problem, just rewrite here, which can be in population or not. When the model and the observer operator are linear, the solution of this minimization system corresponds to the solution of the observer model, which is given here. So it's a time discrete version. So here it's a time discrete version of the model, the classical model. So this is a solution of dynamical model, sorry. And for the observer model, I will add a new terms, which is presented here. And as you can see, this is the observation, and this is a comparison between the observation of the solution of the models. And there is a gain term just here, a gain operator, which is a Kalman filter. And it will work as a penalization of the solution of the model using the available data. If we look on the definition of the Kalman filter, which is given here, we'll see that it depends on W, which is the covariance matrix of the observation error, of P, which is the covariance matrix of the estimation error, which follow, in fact, a Riccati equation, and on H, which is the observation operator. So the matrix P, which can be seen as the covariance matrix of the estimation error, is a full matrix of the size of the solution of our model. So this means that this can lead to prohibitive computational times, the resolution of this part, if we consider large system. If it is not linear, it is classical to rely on approximate optimal sequential estimator. And in this work, we will consider the unscented Kalman filter. So the idea is to replace the nonlinear operator that we have in the Kalman gain by a finite difference approximation, which are based on sampling points. So the idea is to first generate p particles around the mean value using the covariance reduce to the, so not reduce, I'm sorry, just using the covariance. I will make a prediction. I mean, I will apply the models to this particle to compute one time step. I will compute the discrepancy between the observations and the dynamics of each particle, and I will correct my solution using the approximated Kalman gain. So if I consider very large systems, so I mean in terms of a number of equations, but also in terms of the larger of the if it is a large population, for example, I will define a reduced order version of our population Kalman filter. The idea is to consider a SVD decomposition of the covariance matrix given here, where U is a matrix of very small size and L is the extension operator. For a linear operator, this decomposition is stable over time, and the equation on P leads to two systems with admissible computational time, which are given here. In nonlinear cases, we can consider extension of these two systems. And so the only part, for example, you can see the reduced order unsorted Kalman filter in this article. So the only missing step here is to define the initial reduced covariance matrix and the initial extension matrix. And to do that, we consider a clustering approach applied to the observation using the Kalman's algorithms. So here it's, for example, a mean clustering with 12 clusters on H, the number of hospitalization for 94 departments. And I will say that U0 corresponds to the means over the clusters, and L0 will determine how much sorry, not each patient, but each department belong to one cluster. So now I will present you a result to the COVID crisis. So in this case, we are the state variable given here. So T, I, R, A, and H. I will also consider a dynamic on B. I recall you that the objective is to find the shape of B without knowledge. So I will consider in the first approach that B can be modeled by a logistic function. So we're doing the first lockdown, as you can see here. And I can have a winner process in order to take into account the fact that there is an error on B, as I don't really know the impact of the lockdown. I will consider a state transformation using a logit function of the state. And I will estimate dq, the four parameters corresponding to the dynamic of B, and the initial condition, which are given here. In order to estimate the initial conditions, the covariance matrix per department or per region is not diagonal, as you can see here, because I will couple the initial condition with the estimation, the state covariance, initial covariance, which correspond. Sorry, and I will consider, for now, the incidence number of cases tested positive and the incidence number of hospitalized for each region. So our estimation is done in 3 steps. So for the first step, I will assume that B follow a natural transmission rate, which decrease corresponding to a logical function. And I will estimate BM and DQ as chair value in the population and the other parameters of the logistic function and the initial condition. So in this case, there is no winner process on the dynamic of B. This will give me some a priori on the initial condition of B and on DQ and on the initial condition. And I will try to see if I can obtain the dynamic of B without any a priori on it. And I obtain the results which are given here in the 12 regions. So it's very interesting because we can see that it is not so far from a logistic function, but we can see some weakly plateau, for example, in the contest here, or in the Ile-de-France here. And we have tried to make a third step where we add as the model the logistic function and the winner process in order to see if the weakly plateau persists in this case. And here it's a difference between the sigmoid function, the logistic function, and the estimated B. And we will see that we have some oscillation, some weakly oscillations around the mean value. So this helps us to choose a step function in the 4 plateau just given here. This can be explained by the fact that every week the government gives another order or the end of the schools, for example, and maybe it can be explained by that, or maybe it's just a noise of the data and how the data are collected. But it's not possible for us to determine this just using this data. So using this result, here we can compute the effective reproductive number in each region. So here it's the value before the lockdown, the value during the lockdown, and the value at the end of the lockdown, which here you can see that it's inferior to 1 in all the region. And we also compute the attack rates corresponding to the infected proportion of the population which have been contaminated. So here we obtain, for example, around 5% of the population. And our results are very comparable to the results obtained by using different methods in France in the same time. And in order to validate our Kalman estimation approach, we have done an estimation using a classical SIEM approach with a step function for B. And here you have the fit-in curves of incident numbers of cases tested positive and incident number of hospitalized. Here there is the evolutions of the effective reproductive number in the 12 region compared to the national average. And here it's a percentage of population of attack rate, sorry, at the end of the first lockdown. And once again, our results are very comparable to other studies which have been done in France in the same time. So now, since the first lockdown, new data are available. For example, hospitalization and incidence number of hospitalization at a refined level, 90 departments instead of 12 regions. And we have used a reduced order version of our population-centered Kalman filter on 12 clusters. And we have made predictions of the, we have obtained this, the shape of B over all the epidemics, as you can see. So the mean value in all the departments is given in blue. And here you have the standard deviations in red, and some information as the first lockdown, the end of the first lockdown, the 1st of September, the second lockdown, and the end of the second lockdown, and which correspond to the beginning of curfew. So I have used it to make some prediction, because at the end we can see that now B seems to be constant in over time. Not the same value in the whole department, as you can see here, but some quite constant. So I have done some prediction assuming that B stays constant. And for example, I show you two departments, 1 and Essonne, and I have the number of hospitalization given just here, and I have I try to I have okay, sorry. So this day it's Monday, and I have make a prediction to see how many new hospitalization I will have in the 1 week and in 2 weeks, and the results are given here. So I don't know if a new lockdown will arrive in France quite soon, but maybe yes. So to conclude, we have validate reduced order population-based Kalman filter, which is able to deal with mixed effects, able to deal with error models. It is very efficient in terms of computational times. We obtain very interesting results on the first lockdown in terms of immunity and effective reproducer number. And the main limitation of our models is that it does not take into account travels between region or departments. So it's not a problem during a lockdown, but it's a problem when there is no lockdown. As a perspective for the application, we want to evaluate the acceptability of lockdown strategy. So the idea is to look if the decrease of the transmission is more important in the department or in the region where the incidence is also more important. So this will be our first perspective. We want to evaluate also the predicting of second and third waves of COVID using only the information of the first wave. So it's a second perspective. And now, as we have some information about vaccination and warning immunity, we want to integrate it in your model. And concerning the perspective for methodological developments, we will want to see if we can deal with large systems, as for example, a large audio systems or even PD systems. So thank you very much for your attention.
All right, thank you.
If you have any question, of course.
Talk. Yes, for the questions, you can, as usual, you can raise your hand, and I will allow you to talk. So, okay, so Pierre is managed to connect again.
Ah, we lost it.
Yeah, it's
we lost him. So, okay.
All right. So in the meantime, so I was wondering, the way you integrate your data in the model. So if I understand correctly, you have one parameter set for each region, or do you also integrate at the national level?
So maybe I can answer that. So this is really the idea of the mixed effect model. So we do not really, we do estimate a value which corresponds to the national level, but every region has a different value. And but how each region have a different value from another region is constrained by a statistical law, and it's constrained by a normal distribution. So basically, if there is one region that deviates from the population mean in one direction, it means that another region will have to deviate in the other way around. So this basically allows the model to give a different value for every region while keeping a constraint in how each region may differ from each other.
Okay, so I think this answers my question, but and so in this, so the effect, I mean, this variation is in a way it's independent of the region, so you don't take into account the specificities of each region. For instance, the population number or density.
So we account for the population number in the differential equation system. So we account for big N, which is the big size of the population.
Just
but
here.
Yeah, exactly. But for example, we may think that there is a density of population which may vary from one region to another region. You may have also age class, age pile that may differ from one region to another region. And the bet here, which is, I think, achieved because we managed to obtain the same result as people who are actually modeling the age stratification, for example, is that this variability that is allowed from one region to another region accounts for this heterogeneity in many markers, such as age class or density of the population. So that's the bet.
Okay.
You're right.
All right. So David, okay, one message in the chat, but Pierre, if you have to say.
Yes. Can I ask a question now? I have a problem finally, I'm back. I had a problem with the internet at some point. I don't know why, but I don't really it's not clear to me what the meaning of your fit in the end. You propose a value for B of t, transmission rate, and you don't specify anything about the initial value, anything about the parameter. I mean, you may obtain, from what I understand about this, you may obtain several values for B of t depending on the variation on the parameter, the other parameter. So how do you take care of that? It's not just one value for B of t. It's depending on the other parameter, right?
Yes. In fact, our first guess was that the shape of B is a sigmoid function or logistic function. And this means that you can't have models depending on the 4 parameters of the sigmoid and on DQ and on the initial conditions, which are given here.
You don't talk about the parameter of the model itself, the epidemic model.
Okay, so
that's what I'm talking about now.
Yeah, yes, I understand. So maybe this.
So in the epidemic model, I can definitively answer. So you're right that if we estimate jointly all the parameters of the model, we are not identifiable. But here we have a lot of parameters fixed. And at the end of the day, as I mentioned, we just estimate B and DQ. And those 2 parameters, knowing that we do observe a lot of series of data. So we do have 3 markers at least in this analysis, plus it's multiplied by the number of regions. So we have 12 regions and we have a lot of time points. At the end of the day, just estimating B and DQ makes it identifiable. Like you can do an identifiability analysis and the system is identifiable. There is a unique value of B, DQ, and E0 actually here that leads to an unique trajectories. It's a one-to-one function.
Sorry, Mélanie, what's DQ? I know B.
So DQ will be the rate of hospitalization.
Okay, thank you.
It's basically the time you spend being infectious before being hospitalized if you have symptoms.
Right.
So how do you know at first place, the parameter, how do you specify it? Because it's, oh, I see, it's specified from the references here. Okay.
Yeah, so either you pick them.
In fact, it was, most of the time, it's estimated from another model or something.
Yeah, or it's just fixed from observation. In those other paper we refer to, so there is a lot of papers that are just describing some cohort of patients. And for example, they evaluated for the rate DH, for example, which is being fixed. It's just the average day spent in the hospital for someone who has symptoms. And they didn't estimate it properly with a dynamical model. They actually followed a cohort, and then they derived in those papers good values for these parameters. So there are a lot of parameters fixed for sure. But I think we are fixing parameter, but there is no free lunch. Like, we cannot estimate everything, and everyone who is using an epidemic model right now has to fix parameter. You just have to be aware about the assumption you make by fixing parameter. And also maybe do some sensitivity analysis for sure.
Okay, thank you.
Any other question?
Could I ask questions, Jian Hongwu from York, from Canada?
Yeah, sure.
Yes, Mélanie, can you go to the page where you plot the function of B as a kind of sigmoid function?
This one?
It's with one picture. It's fine. Yeah, it's good. Yeah. So
this one, okay.
Okay, yeah. So I think this is a wonderful idea, and so you assume the effective transmission is relatively a step functions with a certain slope of one transmission level to another. And so do you have, for example, the time interval is a parameter you have, the names of each level and the slope is a parameter you estimate, or is really relevant to different intervention, the level or duration of different intervention procedures? You know what I mean? So going from the first block to from the left to right hand side, so that in between that interval, that middle point is something you decide in advance, or you identified from the data feeding? Yes, here it is.
Yeah, so basically the thing is that if you are using classical approach with SIEM, you need to specify the parametric shape of the transmission function, which you don't have to do when you use Kalman filters. And yes, what we did is that from the Kalman filters that you see on the left, we basically inferred that there is kind of a sigmoidal function, but it was easier to go with a parametric function, which was a step function for the estimation with the classical SIEM. And we basically inferred that we needed like 4 steps from the Kalman filter estimation to actually accurately describe the sigmoid. So this is exactly the pipeline. Like, from something which is completely non-parametric, we do infer a parametric shape, and this is what we decided was the best.
And doing the to obtain these results with the SIEM approach, the estimation of this parameter B0, beta1, beta2, beta3 have been done.
Yeah, I understand. You know, there are 4 steps. But do you know how long the step it is, or you infer from Kalman filter? You estimated these names.
We infer from Kalman filter that it was weekly plateau. So here it seems that the period we infer that the period is 7 days. Okay,
so now, so the hospitalization data is about, for example, 2 weeks. Delay from the infection data. So you considered that already, or?
Sorry, the hospitalization data?
I mean, the hospitalization comes about 2 weeks after the infections?
Yes, so right now, if we just sum up, so we have like 2.3 days, I think, being exposed non-infectious, and like something like 4 days being infectious, and hospitalization is about 3 days later. So it makes it like 8 plus 10, so it's 10 days after infection. So I think it's pretty much consistent. It's not 14 days, but in this model, it's like 10 days.
Thank you. One more question. So related to this, this is very interesting because this one our group is trying to figure out how to do it. So have you, once you identify the 4 steps, did you go back to check that this 4 step is consistent with the interventions that each region implemented?
Yeah, so very interestingly, we can speak broader on slide 27. So basically, like the shape that you see here of the transmission a long time for the last year, so the total last year, was inferred completely non-parametrically. So this was just inferred using the Kalman filter, and the Kalman filter is blind to the observation, to the policies. I mean, we do not input this information, and which is kind of funny is that you can see that the lines which are actually materialized, they do represent some change in the policy. And so somehow it means that the Kalman filter, I mean the estimator, in its estimation of the transmission, managed to see that at least there is something happening inducing a change in the transmission. And so if you relate the estimation of your estimator to the interventions that are going on, then you really realize that this mathematical approach is actually underlying different transmission during different periods because of different policies.
Nice.
Yeah.
Thank you.
Okay, so we have one more question from Jeffrey Harris in the chat. He's asking if you can say more about the source of the data parameter R, which measures the proportion of asymptomatics.
Sure. So this was a work we've been doing. So we inferred this from the Sentinel data. So basically the Sentinel data, it's not people being tested, but it's all the COVID-related people, all the people who have COVID-related symptoms in a region that has been seen by general practitioner. So basically it gives a hint about what is the size of the epidemic that you actually do not observe by testing, but it's still there because it's reported by general practitioner. So we use this value to actually have a good value for this parameter, or at least a good guesstimate for this parameter. And so this is from a database, a Sentinel database that we have in France. I'm not sure whether or not it's something that is also available in Canada or somewhere else.
Right, so now what is the range of values for R?
So the range of value of R is very small. So it's from like 3 to 10%, I would say. And those are the value that we took. And so if you go to the article on medArchive, there is a derivation from this parameter to what would be the percentage of asymptomatic, because this percentage is not exactly the percentage of asymptomatic. This will be the percentage, the ratio of people that are tested over all the people reported to have COVID symptoms. So this is not the asymptomatic, but in the paper on medArchive, if you're interested, and we can discuss by email, we derived from this parameter what would be the percentage of asymptomatic, and we find around 20%, which we think is consistent with what has been found on boat ships, and which is also a value which is used by other groups in France at least.
Hi, this is Jeff. I'm calling from, or participating from Los Angeles. It's almost 9 in the morning. Thank you very much for your presentation. the literature I've seen places the percentage asymptomatic at closer to 40 or 50%. And I'm just wondering if you're getting numbers closer to 20 or 30%, what is the discrepancy?
So we could definitely check with a higher rate for sure. But so I didn't review the literature recently. So I must say that last time I did that on this specific parameter, it must be like 6 months ago. So maybe it changed. But last time it was on the Diamond Princess that I've seen the estimate. And the estimate from the Diamond Princess, it was more around 20%. And this is also a value that is taken by a lot of groups in France. So I'm very curious about which reference you have with asymptomatic rates at 40%.
I'll send Pierre the references.
Yeah, sure.
I think there are two papers I found. One says 40% and the other says 50%, but I can't vouch or say that the source of the data used in those papers is more reliable, but that's what I've been reading lately.
Okay, so I'm very interested and maybe we can exchange on this point. I can send you the paper about the Diamond Princess, and definitively they ended up taking something around 20%. And this is also what they used in Pasteur Institute for a lot of paper we had about the epidemic in France, the paper Salge et al. I think they took something like 23%. I can double check and also send to Pierre, or feel free to send me an email. I would be happy to exchange on that topic.
No problem. The Diamond Princess was a closed population in which they were able to interview everybody on the ship. And perhaps they were able to ascertain minor or mild symptoms like feeling achy in your muscles. Whereas in the general population, there will be people who have very mild symptoms who will not seek medical care at all, have no contact with their GP. And I am speculating, but perhaps that is the source of the discrepancy.
Yeah, that's probably right.
It's Jiang Hong Wu again. So I fully agree. I was about to say that the discrepancy is just completely understandable because Princess Diamond, I think every passenger is assumed to be exposed, and so.
Yeah, sure.
Right. So maybe. Sorry, maybe it's time to switch to the next speaker. Okay, so I'll promote Zachary to the speakers, and thank you, Annabelle and Mélanie, for a very nice talk, very interesting.
Thank you.
Thanks.